So we wrapped up talking about measures of center in the last section, and as I mentioned, that was basically aimed at addressing the question, given a data set, what would you call typical for the data set? So our next section kind of addresses like what might be a natural follow-up question. So once you know what typical is, how much do your data and your data set differ from that typical? So if you're talking about something like that, you're really working on what you might call a measure of the dispersion in your data set. Um, so there's one main one that we're going to focus on pretty heavily, but just in terms of sort of an intro, if you were trying to figure out some way real quick just to figure out how spread out your data are, which dispersion kind of points you in that direction, the first thing you might do is try figuring out, well, like what's my biggest data value, what's my smallest data value, and then like figure out the difference between them. If you're doing that, you're calculating what you might call the range of a data set. Some folks might refer to it as spread, but range is the more preferred term statistically speaking. So you could work something like that out. It's not terribly challenging. The upside is that it's relatively quick. Unless your data set is really massive, it's probably not too hard to spot the biggest value and the smallest value, and then it's one subtraction. The downside is kind of everything else. It's quick. You kind of pay for that because you're essentially using only two data values to say something about the entire data set. So in particular, I've provided a couple of examples in the PowerPoint slides, listed in two columns. The bullet points, sorry, I couldn't really figure out how to make that work inside PowerPoint all that elegantly otherwise. The catch is, you can tell from looking at them, they behave quite differently. One of them, 5 of the 7 numbers in the data set are the same. Another one is off that collection by 1, and then you have a 0 sitting way down at the bottom. The other data set wobbles around all over the place. It's got 7 different numbers. But by design, each of them have the same range because the largest data value in each is a 9, the smallest is a 0, so they have the exact same range, but they're behaving quite differently. So ideally, you'd find some way of measuring dispersion that actually uses all of your data values instead of just conveniently grabbing 2 that were easy to get hold of. So that's what we're going to be talking about in particular. Our end goal here is to calculate something we call the standard deviation of a data set. But in order to get that, we kind of get something else first as a result of the process we use to get hold of that standard deviation. So again, it tends to build off all of the values in a data set. So I think it's good to talk about this as we look at a particular example. So I'm going to list out really quickly those test scores from the example that we saw in talking about measures of center. So I'll keep them kind of conveniently listed in order, but anyway. So we'll have a chart that looks something like this. All right. So before we get to the standard deviation, we actually need to calculate something we would call the variance for our data set. As it turns out, once you got the variance, there's basically just like one more button you need to hit on your calculator in order to get hold of the standard deviation, which is the real guy we're after. So this is going to end up using all of our data values as opposed to the range where you just would look at the 98 to 53 and call it a day. It also gives us a measurement, in some sense related to the mean of our data set. So at its core, variance and standard deviation kind of take for granted you already know your data set's mean. So hopefully you recall from last time we worked out that the mean was 82.75 without that fictitious 12 I tossed in there. All right. So that was our mean. Statistically speaking, we would generally refer to it using that notation, x bar. Our textbook will sometimes use the Greek letter mu instead. I like x bar. Anyway, so that's our mean. So what we're going to do is once we've got our mean, we're going to figure out how much each of these guys differ from our mean. That's what we're actually calling the deviation of each data value from the mean. So in the chart, it looks like that, x minus x bar. And God willing, I'll be able to fit these numbers in here. So that guy gives me negative 29.75, negative 8.75, negative 4.75, a pair of 3.25s. Let's see, that one should be 9.25, 12.25, and then at the end, 15.25. So those are my individual deviations for these particular values, okay? So like I said, all I'm doing here is subtracting the mean from each of these values in turn. Now, you might end up thinking, well, what if we like average those deviations? That's an interesting idea. I will save you the heartache though of trying to do that because you're going to get 0 back if you know done things correctly. Because sort of by design, some of these are positive, some of them are negative, and yeah, that they end up canceling each other out. So the average of your deviations, assuming you didn't like round off or something, is going to give you 0. So we need to try to find some way around that problem. The way statisticians conventionally go at this is it's kind of tricky to work around. So we're going to end up squaring each of these values. Now, the good news is that when you square a number, whether it's positive or negative, the square should come back positive, because negative times negative would give you something that's positive. All right. Now, this is a little clunky in this instance because I used a real world type data set rather than something conveniently designed to make the calculations easy. So I'm not going to be doing any rounding off here because I want stuff to be as precise as possible. If you wanted to round, you could, but you'll end up off a little bit, later on. So bear with me for a moment. So when I worked these out, I got 885.0625. So 885.0625, 76.5625 for the next one, 22.5625, and again the negatives are gone because squaring a negative number should give you back something positive. We have a pair of 10.5625 values. Let's see, this one I got 85.5625. You may sense a bit of a pattern at this stage. It turns out it breaks with this next to last guy. We have another 0.625. And then the last one, it ends up having a 5.625 at the end again. All right, so I calculated all these deviations. I've squared all of them, okay? With me so far. All right, so now that I've worked out the squares of these deviations, now I'm going to do something kind of like averaging them. So I'm going to add all of these guys up. When I do that, assuming I've done my arithmetic right, and I've done this particular example enough times that I'm pretty sure I did, I would get 1,473.5. All right. Now, if we were averaging, you'd normally think we divide by the total number of data values we have. We divide that guy by 8. And in the right circumstances, maybe you would. For the purposes of Math 107, we're actually going to divide by 1 less. I don't want to get too deep into the technicalities of that. We're actually dividing by what you call a number of degrees of freedom. Don't feel like you need to look that up. That doesn't come up anywhere else. But so we're going to divide that guy by 1 less. So instead of dividing by 8, we divide by 7. And that is, in fact, what we would call the variance of our data set. Variance is conventionally denoted with a lowercase s squared in this instance. And if you work out that division, we get 210.5. All right, so that's our process. I like looking at it laid out step by step as a process. You'll see this process laid out in the PowerPoint slides. I like that better. The textbook actually provides like a formula you can look at, but to be honest, I think that formula is kind of scary looking, so I think it's easier to get at your variance if you look at it as, I do this, then I do this, and you kind of look at it as a series of steps rather than a big formula that I have to spend a while explaining notation and stuff. Anyway, so here's our variance. But I said before, the variance is really just kind of a stepping stone for us. We really want the standard deviation. So standard deviation is typically represented with just an s instead of an s squared, which may kind of point you at what you need to do to get it. Yeah, we take the square root of what we just worked out for the variance. 210.5 sitting under that square root radical or behind the square root button on your calculator, however it works out. I got a standard deviation of approximately 14.51. All right, So that's our process. As it turns out, there's actually a different route that will get you to this same value for your standard deviation. Technically, it gets you to the variance, and then you take a square root. But um, unfortunately, this data set, as I said, it has the benefit of being kind of real worldish, but it's kind of a pain to work with thanks to all these awkward numbers. So in another video coming up right after this one, I'll take a look at this both processes with a slightly more convenient set of data values. So, keep on watching.